Hello, everyone. This is the third of 3 videos talking exclusively about sequences. And our goal in this video is going to be just to introduce a little bit more terminology to see how we discuss sequences and how we can use properties from this discussion in order to infer whether or not a sequence is convergent or not. So let's go ahead, let's jump right in. This should be a relatively brief video for us. So what we're going to talk about today are bounded and monotonic sequences. So let's start with the definition. What does it mean for sequences to be bounded or monotonic? So let's start with boundedness. So a definition, a sequence AN is bounded from above, red, is bounded from above by, if there exists some number m, so a number m such that an is less than or equal to m for all n. And in this case, m is called an upper bound on the sequence, an upper bound for the sequence. So you can probably imagine what's coming next, right? The next piece is going to be talking about lower bounds as well. So we can say that a sequence AN is bounded from below if there exists a number, let's use little m in this case, such that AN is greater than or equal to little m for all n greater than or equal to 1. And in this case, m is called a lower bound. Pardon me, a lower bound for the sequence AN. So a lot of writing for now. We need to establish our definitions. And in particular, if you put both of these together, if you're bounded from above and from below, then you say that the sequence is bounded. So finally, if the sequence AN is bounded from above and from below, then we say that the sequence AN is simply bounded. So is bounded. And then the final piece of this, I know it's a long definition, bear with me. If AN is not bounded, so if there does not exist either an upper or a lower bound, then it is an unbounded sequence. So that was a long definition of a lot of stuff, but this is a fairly common idea, right? We've talked about this with functions before. The idea that a function is bounded, you have sort of the exact same idea. It's that you can put a roof on the function and you can put a floor on the function. And so that would give you, bounded above and bounded below. You put these two things together, you say it's bounded. It sort of has to lie in the interval minus little m to, in little m to capital M. And so let's just talk about some examples here. So example, the first one, AN equal to, say, n. This thing has no upper bound. Why? Well, if you told me there's an upper bound, I can always just find an integer n that's bigger than that. But an is bounded from below by 1. Why? Well, the first element in this case is 1, and then the next one is 2, and then 3, and you're just continually adding up. So the first element in this sequence is the smallest one. Okay, let's look at another example here. So if an is equal to, let's say, n over n plus 1. So this gives me a1 is equal to 1/2. A2 is equal to 2/3. A3 is equal to 3/4, and so on and so forth. We can see that an is greater than or equal to 0 for all n, which tells us that an is bounded from below. Maybe we should put the sequence notation, bounded from below. And similarly, an is less than or equal to 1. And in fact, it's actually strict, but I just put less than or equal in there because a number divided by the next number in the sequence is always less than 1. So this tells us that an is bounded from above. And so it's bounded from below and it's bounded from above. This says that the sequence an is bounded. So you're probably pretty used to this idea from calculus, right? It's the same sort of thing that we use for functions. Now, I'm going to put a statement in here. And I think it's fairly intuitive. I'm not going to prove it, but I urge you to try and prove it. So if you'd like, maybe pause the video and try and think about how to do this. But convergent sequences are bounded. So sort of what's the intuition here? Well, the intuition is that convergent sequences sort of they focus around a single point, the limit L, right? And so that doesn't give them the opportunity to get too far away from L. And so that's sort of where the intuition comes from here, right? You're never going to be able to go up to infinity because everything is sort of staying around L. Same thing, you'd never be able to go down to minus infinity because everything or most of everything is staying around L, just from the definition of convergence. So this is an important property, but it sort of confirms something that we already knew. Okay, so what we saw actually with this first example here is that my sequence is actually increasing, right? It went from 1, then it went to 2, then it went to 3, then it went to 4, and so on and so forth. And again, we have a way of talking about these kinds of sequences. So let me give you another definition here. And let's say a sequence an is said to be, and I'm actually going to write this in point form because I think everybody's getting tired of writing these long definitions. So let's start with non-decreasing. And so non-decreasing, if an is less than or equal to an plus 1 for all n. And so essentially that tells you that a1 is smaller than a2, which is smaller than a3, is smaller than a4. And then clearly you have the opposite, so non-increasing. If an is bigger than or equal to an plus 1 for all n greater than or equal to 1. And both of these together fall into a category of what's called monotonic. So monotonic. And basically this is the sequence an is either non-decreasing or non-increasing. So either non-decreasing or non-increasing. So one of the above, we would call this thing a monotonic sequence. So my monotonic sequence, or my non-decreasing sequence, an equal to n, 1, 2, 3, 4, 5, whatever, that thing is non-decreasing and therefore it's monotonic. So let's note that as our first example here. So our example 1, well, an equal to n is non-decreasing. And so monotonic. Okay, let's look at another one. Well, the second example we did was n over n plus 1. In this case, this thing is also non-decreasing. Right? We saw it went from 1/2 to 2/3 to 3/4 to 4/5 to 5/6 and so on and so forth. And it's increasing up to its limit at 1. So, and so monotonic. Okay, sorry, 3. How about the sequence an equal 1 over 2 to the n? Well, in this case, you basically get, so if we work this out a little bit, an plus 1 is equal to 1 over 2 to the n plus 1. That's just the definition. You can factor out a 1/2 here, and you get 1 over 2 to the n, which is 1/2 of an. Now, if you take half of a number, that's going to be smaller than the original number, assuming what you started with is positive. So this tells you that an plus 1 is strictly less than, but I'll write it as less than or equal to an, which implies non-increasing. So again, non-increasing, and so again, it's a monotonic sequence. Okay, let's do one that might look silly, but it probably merits some investigation. A constant sequence. Well, we have first an is equal to 3, which is less than or equal to 3, which is less than or equal to an plus 1, which tells us that we are non-decreasing. But also you can sort of repeat that argument and you can say an equal to 3, which is greater than or equal to 3, which is equal to an plus 1. Sorry, this should be an equality, of course, which tells us that I'm also non-increasing. And so you can actually prove that a sequence that's both non-decreasing and non-increasing has to actually be constant. And we're seeing that in action right here, right? This constant sequence is both non-increasing and non-decreasing. It's like super monotonic because it's constant. It's not going anywhere. All right. So then let me give you one more example. Let's do an equal to -1 to the n. So this gives me a1 is equal to -1, a2 is equal to 1, a3 is equal to -1 again. Well, you can see that a1 is less than or equal to a2. So that would get us on the path to start thinking about non-decreasing. But also, a2 is greater than or equal to a3. And so that would get us on the path to starting to think about non-increasing. But because a2 is involved in both of these, this implies that an is not monotonic. Right? Because it doesn't keep up with increasing or it doesn't keep up with decreasing all the way through. Okay, so sometimes when it comes to monotonic functions, you can use these properties to prove that a function converges. So it might be slightly easier than evoking all of the work that we did in the previous example or the previous video to simply evoking what's called the monotone sequence theorem. So the monotone sequence theorem. And basically what this says is that if a sequence AN is bounded and monotonic, so putting both of the definitions that we learned in this video together, bounded and monotonic, then the sequence converges. So this, again, should be fairly intuitive, right? So imagine the sequence is non-decreasing. So AN is less than or equal to AN plus 1. So each time you're sort of incrementing upwards, but also you've got a ceiling, right? There's only so many floors up you can go because you're bounded. So you're sort of increasing up until eventually you sort of stagnate because you're fitting infinitely many points into this, you know, along this sort of stairwell that has to be getting less steep. Okay, so that's sort of the intuition here. And, you know, this tells us, again, something that we probably already knew, but what we were able to do in this video is put definitions in place that are going to allow us to speak about sequences as we proceed through our discussion in the next videos. In particular, we got a new convergence criterion, the monotone sequence theorem, that tells you, you know, if you have a monotone and bounded sequence, it has to converge. And again, you should always just use this intuition that I just gave you. If you're increasing and you've got, you know, a roof on how far you can go, then, you know, you had to stop somewhere before the roof. That's all it is. So it's a brief one today, but we introduced some new ways of thinking about sequences and new ways to talk about sequences, and we improved our language for how we can understand these things.